Well, good morning. It's 11:31, 1 minute late getting started with linear algebra. Sad news is I'm the only one in the room, so hopefully others will be coming in. So I'll go on and get started with class, wait on the announcements until some of the others get here. We're in chapter 4, which is vector spaces, and we're in section 4.3, subspaces of vector spaces. We got started on this last time and got through example 4 on page 164, and then starting on example 5 on that same page, 164. Apologize for my voice. I'm still having difficulty with this cold, but every day it seems to get a little bit better. But my throat is very slow coming back. So anyway, example 5 on page 164 is talking about subspaces of functions, which is more of a calculus application of subspaces. And here they start with, let W5, let me get my pen set up. Okay, let W5 be the vector space, VS is vector space, of all functions defined on 0 to 1. That's inclusive. Okay? And let W1, 2, 3, and 4 be defined as follows. Okay? W1, the set of all polynomial functions defined on 0, 1. Okay? W2 is the set of all functions that are differentiable on 0 to 1. Okay? Now, certainly all polynomial functions are differentiable, but not all differentiable functions are polynomial. So W1 is a subset of W2. Okay? W3, the set of all functions that are continuous on 0 to 1. Okay? Now, of course, all differentiable functions are continuous, but not all continuous functions are differentiable. Think of the absolute value function. It's continuous for sure, but at the vertex of that v, which you always have on a absolute value function, well, let's see, that wouldn't be a good example on 0, 1. Absolute value of x plus 0.5, that would do it, or something like that. Okay. W4 is a set of all functions that are integrable on 0 to 1. Set of all functions of integrable. functions defined on 0 to 1. Okay. Now, let's think on that one for a moment. Certainly all continuous functions are integrable, but not necessarily all integrable functions are continuous, because you can integrate functions on different subset of domain that would not necessarily be continuous. Okay? So, and then W5 is a vector space of all functions defined on 0 to 1. All functions, whether they're integrable, continuous, differentiable, polynomial, or what. All functions. Okay. Now, and I think I've just, because I just said all those things, I basically just defined that they're all subsets of one another. But all they're asking for here, and we've just said that they're all subsets, so we've said that. But they also say that Wi is a subspace of Wj for every I less than or equal to j. Okay? Now, that means that all these, including W1, is a subspace. Okay? Well, certainly the polynomial functions, okay, you got a set of all polynomial functions defined on 0 to 1. All right. Of course, the two things that have to be true are the closure of vector, or this would be function addition and scalar multiplication of a function. And if the function is defined on 0, 1, let's start with the simplest one, polynomial. Any two polynomial functions you add together will be a polynomial function, okay? And if they're both defined on 0, 1, they'll be defined, the sum will be defined on 0, 1. So that one's okay. And if that one's okay, oh yeah, and then the scalar multiple, any polynomial function you multiply by any real number in the world, you're still going to have a polynomial function defined on 0, 1. So therefore, it's closed under scalar multiplication. Now, I always like to go back and also note that the 0 function is included, and the 0 function is a polynomial function, f of x equals 0, that's defined on 0, 1. In fact, it's defined everywhere, and so no big surprises there. So if that's a vector space, and all the W1 is a subset of W2, W2 is a subset of W3, and W3 is a subset of W4, and W1 is a subspace, and W4 is a subset of W5, then every one of these is a subspace, okay? Because everything that's in W1 is in W2, so everything still fits. Okay. Now, you can read through their solution, and hopefully you'll see everything that we've already talked about. Maybe a little more, okay? Note in example 5 that if U, V, and W are vector spaces such that W is a subspace of V and V is a subspace of U, then W is also a subspace of U. The special case The next theorem tells you that the intersection of two subspaces is a subspace, and they're going to show that in something like a Venn diagram. But here is that next theorem. I'm going to start with a clean slide. All right, good deal. He's here. Charles is
Sorry
here.
about Tuesday.
No problem.
Wrapped up in work.
Yeah, I figured. All right, let me pause for a moment here. I just cleared the screen so you can't see what I was just talking about. Turn on the projector. Turn on the light. And start with the announcements, because when there's no one in the room, I don't see any reason to make any announcements. But now they'll have to listen to YouTube video to get the announcements. Let me first with the paper announcements. I did find out there is a coach here at Lawson who is named Jefferson, Coach Jefferson, John Jefferson, and he sent this email about a company named No Kid Hungry. He gives the company description. The job title is Brand Ambassador. Job description has a couple of bullets on that. It says interested candidates should contact Henry. Doesn't give a last name, but gives an email address, and it's HS with 7 digits. So that must be Henry S. something, for more information. The weekly wages are $350 a week, and so it sounds like a great sort of entry-level job. So if you know anyone who's looking for work, looks like this might be a good possibility. Okay? I figure you have a busy enough job that you probably don't want that one. All right. And then secondly, I think I announced this one before too. Now, it's not just at UAB, but this is one sample is at UAB. The National Science Foundation sponsors these programs that major universities propose to do if their proposals meet National Science Foundation standards. Then they may get a grant on it. UAB has gotten one for several years, and these are called Summer Research Experiences for Undergraduates. They usually shorten that as REUs, Research Experience for Undergraduates. They're always, I think, in the summertime. This is 2020. Now, there's the flyer from 2019, that one there, the middle one. They sent one for 2020, and I can't find it. Unless they sent me an old one, but I didn't think they did that. In fact, I thought I put it up right over there, and then I read that they wanted it in a high traffic area, so I thought I took it down to Career Services for them to post, and they can't find it. So, but same information there, except the dates and stuff are probably different. But anyway, it's a repeated one, so theirs is experimental and computational materials research. They offer a broad range of interdisciplinary materials research experiences to undergraduate students with diverse backgrounds in physics, chemistry, applied mathematics, and engineering. Well, that's not all. You'll see later computer science should be listed there too. Probably some others as well. I think maybe even biology. Okay? The research projects include, but are not limited to, electronic materials, nanomaterials, lasers and optical materials, biosensors, biophysics and biomaterials, and computer modeling. The scientific research projects are developed specifically for undergraduates by an interdisciplinary team consisting of science and engineering faculty from UAB. The application deadline, there is a website you can go to and find out a lot more information. The application deadline is March 15th, and decisions will be made no later than April 15th. So you got plenty of time. It's a good idea to do. The dates on this are May 17th to July 24th, which I think is about 10 weeks. Okay. So anyway, you're welcome to see this, get the website, phone numbers, there's email for people, various people on that. All right, that takes care of outside. Now, inside, as in Lawson. I've been asking for weeks, are we doing student course evaluations? They never had shown up until late Monday afternoon.
I did mine
Excellent.
for this class, but I didn't do one for, they sent me two. One for this class and one for my advisor.
For what?
For my academic advisor.
Okay.
And I didn't do that one. Well, I made a mistake after I completed yours. I deleted the email where it came from. So they'll probably send it back just to give you that one.
Sure. No guarantee, but in your email, can't you find deleted? Go to the deleted box?
Yeah, I will.
Yeah, look there.
I didn't think about that.
I do it way too frequently, so I know that one. Okay.
Yeah, I did do that for this class. I did that first.
Yeah. And please do the others too, because I get feedback from you every time we're in class, whether you realize it or not, verbal, nonverbal, whatever. But sometimes other things don't get that kind of like your advisor. So do that. I'm not your advisor, am I?
No, sir.
Okay. I'd say if I am, I got feedback from you there too. Other people, they may not. Okay. So please do the student course evaluations. They are out there. They're open finally. Just this week they've been open. So please do those. You have until the end of the term, like the end of finals week or maybe even a little later, but don't put it off. I remember when I was an undergrad, once I took that last final, it was like, remember the little thing they used to use called Etch-a-Sketch? You could draw pictures on it and then turn it over and shake it and it would disappear.
Oh, yeah.
Okay.
Yeah.
As soon as that last final was done, it's sort of like I took my brain, shook it, and I was out of no longer thinking about things like evaluations and stuff. So please do them before you forget about them. Okay. All right. Let's see. Now, let's talk about this class now. I'm trying to think if there's anything at school-wide. I've received one paper out of the three, so please get your research papers in. Technically, today is the last day. I can receive it without you losing points, so please get them in to me today or as soon as possible, okay? I've gotten both of your first tests, don't have the other's first test. I've gotten both of yours second test. I don't have the other second test. I've received one test 3.
Yes.
Okay. Yeah. So please get me your other test 3. And at the end of the class today, I'll be giving you the 4th test and let you know how much of it, because I had to make it out before the class was. So we'll see how far we got. Okay, here it comes. Test. Good deal. Thank you.
Yeah, chapter 4 is long. We would have made it to the end.
What's that?
Chapter 4 is so long, we never would have made it to the
Oh,
end.
no way. But we'll get as far as we can. Before I forget, let me get. And I don't know if you remember, but for some reason, early in the term, because I didn't have her the whole term, my work study student was, had been cleaning out some old files. She just decided to clean out a current file and put I think both of your first tests in the shredder. So, I mean, not in the shredder, but in the shredding box, but it's locked up and we couldn't get it out. So, I'm having to remake, and not just yours, the keys, the new test, I'm having to redo all the tests and keys and everything else. So, I can't return all your work to you. And I'm going to give Peyton all the time he can to get his in, but when you come turn in your last test, I'll try to give you everything back. I think by that time it'll be too late for him too. So when you do, bring that. So, like I said, I'll be giving you your test 4, chapter 4, whatever it covered in chapter 4, test at the end of the class today. I'll let you know which questions are optional and which ones are required, because we probably won't cover everything in it. Okay, next. When are they due? Anytime next week. In fact, this week too, if you want to. But let me tell you where I'll be and when I'll be there. Okay. Today I'm here until 8 o'clock tonight. Okay, now I'll be in class part of that time, but the rest of the time I'll be around my office until 8 o'clock tonight. Or near 8. Maybe not quite 8, but close to it. Okay, tomorrow, normally I'm on the Birmingham West campus. However, I have a doctor's appointment tomorrow at 9:20. So I'll go to the Birmingham West campus. I'll only be there from 8 to around 8:40 because it'll take me, I usually allow 30 to 45 minutes to get back. And I've got to park and get everything else. So I will be leaving there about 8:40. Now, I would like to think I'll get back after my appointment. However, this is my annual physical, which was scheduled originally for last spring. But the doctor's office called like a week before and said, I don't remember what it was, he was going to be out of town or for some reason he had to reschedule. He wouldn't be available whatever day it was. So could I reschedule? I said, sure. When? Well, she said, well, the next opening is either September or October, or October or November. What? And she was putting me down for a weekday. I said, is there any way I can have it on a Friday? Because I have classes during the week, and I don't have classes on Friday. She said, oh, well, the next Friday will be December 6th. So that's why it's my annual physical, which is almost a biannual physical now, because it's been almost 2 years since I had one. So I don't know if he's going to be wanting blood work, if he's going to be wanting any other tests or anything else. If he does, I probably won't be back before 12. Okay? If it goes real quickly, which it does sometimes, then I'll probably be back. I can't imagine I can get back there before 11, but if I can, I will. But if it's after 11:30 when I finish with the doctor, by the time I get back to campus, I'll be turning around and going back home again. So I will, don't know about the last part. First part, I'll be there from 8 to 8:40. That's all I can guarantee. I'll try to get back there between 11 and 12, if I can. All right, that's tomorrow. Next week, Monday of next week, all my classes have take-home finals like yours are, and so I'll be in my office basically from 8 till 6 next Monday. Tuesday, I have a final down the hall here in room 205 from 8 to 10. So I won't be in my office from 8 to 10, but I'll be down there from 8 to 10. It may go after 10 because it's a big class, and sometimes some of them take longer. So I'll be there as long as it takes. After that, I'll be in my office until 3:15. Well, a little before 3:15, because I have a class in here at 3:15. Not the final class, because it's a mini-term class. They have class the first day of finals week and then have the finals the second day. So we have class at 3:15. So I'll be in my office a little before, probably up until maybe around 2:45 or 3. Then I'll be up here. I've got to go off campus just real quickly, but I'll be back pretty soon. Okay, and that class, I'll be returning all their quizzes, all their labs and all their tests to them. So that takes a while. And then they'll be doing their last lab. That could take up to 2 hours, but probably won't. And then they've got their last test, okay? And that could take maybe another 30, 45 minutes or so. So I could be in here from 3:15 until, say, 6. It could be earlier. It could be later. But then from 6 to 8 or whatever time I finish here, back in my office till 8 o'clock. That's Tuesday. Wednesday, no finals on this campus, so I'll be here from 8 until 4. But at 4 o'clock, I'll leave to go to the Birmingham East campus because I have a physics class. They'll be turning in their finals from 4:30 to 6:30. So I'll be over there from 4:30 to 6:30. Between 4 and 4:30, I'm traveling over there. So I'll be available here 8 to 4 and over there 4:30 to 6:30. And that's on the East campus in the nursing building, room 103. All right, that's Wednesday. Thursday, back on this campus from 8 o'clock in the morning until 3 o'clock in the afternoon. At 3 o'clock in the afternoon, I have my mini-term final. Now, some of them are going to take it early because they're either graduating or have travel plans or whatever. But anyway, those that are going to wait until Thursday to take it, I'll be in here with them until they finish. Probably not going to take more than half an hour, 45 minutes for them to finish if they get here at 3. But some of them work and do other things, so they may be a little later getting here. So I'll be up here from 3 o'clock until they finish. Then I'll be back in my office until 8 o'clock. Then next Friday, not tomorrow, but a week from tomorrow, I'll be on the Birmingham campus from 8 in the morning until 3 in the afternoon. However, that 1 to 3 is graduation over there. So I won't be in my office. I'll be on campus, but not in my office. I'll guarantee to be in my office from 8 to 12. Now, I'll stay in my office as late as I can, but they usually want us over in the gym before graduation begins so they can make us stand around and wait for a while. Now, line us up and do all those sorts of stuff. So I don't know how late I'll be in the office. I'll be there at least till 12, and then we'll be there until they make us go to the gym. And then from then, I'll be in the gym until graduation's over, and then I'll be going home. So now, that ends next week. Grades are due in by noon on the following Monday. So I'll be here on this campus on Monday, and I'll be finishing my grading and getting everything in from 8 till 12. I think it's noon is usually when they're in. Now, afternoon, I'll be here until 6. So I'll be in my office then. So if you don't have everything in by noon on Monday, you're getting it incomplete, okay? If you get it to me anytime after that, I'll change the incomplete to a grade, okay? Now, Tuesday and Wednesday, we're still required to be present on campus. But in the old days, they let us work in our office and get ready for the next term. More recently, they've started planning meetings then, which is really ridiculous. But if they do that, then I may be on the Birmingham campus. I don't know. They haven't told us yet. So Tuesday and Wednesday, I will be on campus. I just don't know which campus or where I'll be. But I will be on campus. So you can get in touch with me, and I'll let you know where I'm going to be if you need to get to me. After Wednesday of that week, that's not next week, but the following week, I'm not here at all until after the new year, okay? So, just to let you know where I'll be and when I'll be there. Any questions?
So if we bypass you or miss you in between
Say this again.
If we bypass you or miss you in between this time frame, will we just fly our test under your office door?
That would be perfectly fine. Or papers, whatever you got under there, okay? My office is 265. And drop off anything there. If you can't find me here or if I'm on another campus, that'll be fine. If it's there Monday morning of the week after finals, I'll have time to grade it. I'll get here by 8. I'll have time to grade it and get your grade in. But sooner you can get things in, the better. But I will be able to manage everything up until Monday morning. Monday afternoon, it's already too late. You're going to get it incomplete, but get the stuff to me. I'll change the incomplete to a grade. All right. Now, before y'all got here, I'd already started in where we left off before. We're in Chapter 4, Vector Spaces, 4.3 Subspaces of Vector Spaces, and I just finished doing Example 5. It's pretty clearly put out in the book, so and you'll hear it on the YouTube video. I was down to the place where it's theorem 4.6, and they had mentioned this earlier, and I mentioned it. Here is theorem 4.6. Okay. Any questions before I get going on this? Okay. The intersection, okay, let's start it this way. If V and W are both subspaces, SS are subspaces, not Nazi Germany, okay? Subspaces of a vector space, VS is vector space, U. Okay? V and W are subspaces of a vector space U. Okay? Then, that implies that the intersection, now the intersection is usually given by the upside down horseshoe, okay? That symbol there. The intersection of V and W, the other is V intersect W, and that's what they show it as, is also a subspace of U, of U. Okay? Now, they have this little thing, it's sort of like a Venn diagram, okay? Here is your, they call it the universal set U. Whatever you're taking this vector space is, it's part of that, okay? Now, V is a subspace of U. W is a subspace of U, and this is V intersect. Do that about half the time when I'm writing an intersection symbol. I make it an A because it starts out like an A, intersect W. Okay? Now, so if V and W are both subspaces of a vector space U, then the intersection of V and W is also a subspace of U. Okay? Now, I don't know if you have a reasonably good feel for what subspaces are yet. Work with them as much as you can to get a good feel. But remember, a subspace has to obey those two closure principles. The adding of the two elements, whatever, we're going to call them vectors because they're called vector spaces, but they don't have to be vectors. The addition principle has to be met, and the scalar multiplication principle has to be met. Now, that usually will incorporate, but I always worry about the zero vector, because that's a thing that will sneak up and bite you. The zero space has to be there. Well, if V is a subspace, that means it's a vector space in itself, and W is a subspace, meaning it's a vector space in itself, then they both, everything in V and in W will meet those 2 and 3 criteria if you count that third one. But that thing about the zero vector, whether it's a vector or not, it has to be common to both of them, and it has to be there for both of them. It's in here, so that's going to be fit. So guarantee that one's met. Then the others you have to worry about are the sum of two vectors in here, and the scalar multiple of two vectors in here. Yeah. I can't wave my arms and produce that. I can for the zero vector, but I can't for the other. So they go into a proof here. And notice they both contain the zero vector because they have to be as a subspace. So we know that V intersect U is non-empty, okay? especially if you draw it like that. Then, because they're both subspaces, they both have to be closed under addition. Every element in it, so everything works. They walk through both of those and they do work. All right. I know that's really not a great proof. Read the book and it does a little bit more, but it meets those criteria, and that's what you have to do. All right. Now, let's move to subspaces of Rn. Okay? Any questions on this before I erase it? Okay. Now, remember what Rn is. Okay? The N is sort of a superscript. R1 is any line, any straight line. That's R1, one dimension. R2 is any plane. Okay, 2 dimensions, length and width. R3 is space, length, width, and height. Okay? But Rn could be any dimension, any finite dimension, not infinite, but finite. So it could be R7. I don't even know what you call those dimensions, but it's represented by a 7-tuple, okay? V sub 1, V sub 2, V sub 3, V sub 4, 3 sub 5, 3 sub 6, 3 sub 7, 3 sub 3 7, okay? And any 7-tuple will be in R7. So this will be any n-tuple will be in Rn, okay? Now, Rn is a convenient source for examples of vector spaces. The remainder of this section will be devoted to subspaces of Rn. So we're not doing matrices anymore. We're not doing functions. We're not doing polynomials. We're not doing any of those. Those are all legitimate. We're going to stick with Rn now. Okay? So that's what we're focusing on. Example 6 says, which of these two subsets is also a subspace of R2? So now we're starting, example 6 is R2, a plane, any old plane, okay? Here's A. The set of points on the line x plus 2y equals 0. Okay? B, the set of points on x plus 2y is equal to 1. Okay? Which of those two, or both, or neither, is a subspace of R2? We know they're both subsets of R2. Which of those is a subspace of R2? A, B, both, or neither? B what? B? Why do you say that?
Well, because I went by the 1. So I guess if they say the same as 0, then that's the case.
Okay.
Now, I went by the product of the number, 1 instead of 0, but I guess it could be either 1, A or B, because they're both vector coordinates.
Okay. All right. Now, I think what I hear you saying is that if a point satisfies this and another point satisfies this, then adding those two together will also satisfy this. Is that what you're saying? Okay. So give me a point that satisfies that. You may have been saying it. I couldn't hear it for sure. 1, 0. Okay. And give me another one.
-1.
-1.
And 0. Last 2.
Say again?
2.
I think 1 would work. Doesn't it? If you have -1 plus 2 times -1 would be 2. -1 plus 2 is 1. So that works. So both of those work. Okay? Now, would the sum of those also be in this space? Okay? The sum of these would be 0, 1. Not in that space. 0, 1 does not work. Does it? Okay? All right. So I think we can rule out B. Okay? I believe you can also rule it out because any multiple here, say 2, multiplying that gives you 2 0, that's not inside space. Okay. So I think you can rule out that one. And yet another one, the 0 vector is not in that space. So no, it's not a subspace. It's a subset for sure, but not a subspace. How about the top one? Would that work? Give me a point that will work here. Say again? 0, 0. Right there we've got a 0 vector, so that works. Give me another one. Say it a little louder. 1 and negative 1 won't work. 2 and negative 1 will work. Won't it?
Yeah, I didn't say. He said 1/2.
Oh, I'm sorry, I can't hear. Okay, you said 1/2 and negative 1. That certainly will work. Okay? And 2 and negative.
Well, I meant like 1 for x and then negative.
Okay, right. Okay, no, that the one I wrote down won't. I was just saying that won't work. Okay, you said it the other way. Which one did you say first? 1 and negative 1/2. Is that what you said? Okay, good. All right. Now, those two will work. And certainly, you add either of these to that one, and that works too, because you've got the same thing. But how about adding those two together? 3 and negative 3/2. That will work. Okay? How about a scalar multiple? I'm going to multiply by that one. Give me a number. Any number. Not 1. Okay?
30.
30?
3. No,
3,
3.
3, okay. 6 and negative 3. Yeah, that'll work. 6 minus 6 is 0. It looks like it does. So this one is a subspace. This is a subset, but not a subspace. Okay? Does that make sense? Okay? So in general, which you have already been seeing, the general rule here would be to make it work, you would have to have of the form negative 2t t. Or the way y'all were doing it, which is fine too, is 2t negative t. That works too, okay? Either one of those generic forms, or you might say parametric forms, would work. And you see any sum of those and multiple of those and stuff like that will give it, and it has a 0 vector. All right. Now, of the two lines in example 6, the one that is a subspace is the one that passes through the origin. That's characteristic of subspaces of R2. That is, if W is a subset of R2, then it is a subspace if and only if one of the three possibilities are true. Now, I'm going to have to, I think, right, can I go on and erase these? Well, let me do this. Here are the, okay, now that should be passing through the origin. Those are two parallel lines. One of them is this one is that one, and this one is that one, okay, where that passes through 0, 1. Okay? They look very similar, however, only the bottom one is a subspace. The top one is not. namely because it doesn't have the zero vector on it. That's the easiest reason to say, okay? But we say there were other reasons too, okay? Now, so based on that, okay, of the two lines there, one is a subspace, is the one that passes through the origin. It's characteristic of any subspace of R2. That is, if W is a subset of R2, it's shorthand for subset, then it is a subspace. SS is subspace. If and only if it has one of the following three possibilities. One, first, W has to contain zero, zero. Has to pass through the origin. Okay? Oh, I'm sorry. Correct that. It consists only of 0, 0. Okay? Now remember that the zero vector may be the only element in the set. It's always a subspace. Because you can add the zero vector to itself, you still get the zero vector. You can multiply any scalar by the zero vector, you still get the zero vector. And it has a zero vector. It is a zero vector. So that's one. And that's pretty trivial, right? Very trivial. Okay? Number two. W consists of all the points on a line that passes through the origin. W consists of all points on a line that passes through 0, 0. Any line that goes through the origin would, if W consists of all those points, then it is a subspace. Number three, W consists of all R2. Okay. Now remember that was the other trivial one. Okay. If W is the entire R2, then of course it is a subspace also because it is R2. Okay. And R2 is a space, vector space. So that leaves you with either the very trivial case, only the zero vector, or everything in there, or the only sort of non-trivial case, and we talked about that last time, I'm pretty sure, didn't we? I'm teaching so many classes I can't remember. Yeah, it's called a proper or non-trivial subspace. Because number one, the zero vector alone is always a subspace, and everything in V or W or whatever, R2, that's a subspace of itself. All the others, other than those two, that are either only the zero vector or all the others, those are called proper or non-trivial subspace. So the only non-trivial subspace is that one. All the points on a line, as long as that line goes through the origin. Okay. So, they do it graphically. Here is your space, all of R2. Everything on R2 is your vector space. Okay? Now, they pick one, as they said, the unit circle. This is 1, 0, 0, 1, minus 1, 0, and 0, minus 1. That's not a subspace. It's certainly a subset, not a subspace. Why? Well, the zero vector is included. Okay? And you add this one to that one, you get something outside. That's 1, 1. Or this one to this one. Or anything else. I mean, so no. That's not a subspace. Okay? That, on the other hand, is a subspace that consists of only the zero vector. And that is a subspace. It's a vector space. Everything fits. Okay? Next, any line that passes through that is a subspace. Not curve, line. Straight line. Okay? And then the only other possibility is everything. All of R2 is a subspace of R2. And that's pretty trivial too. So this is a trivial one. This is a trivial one. The line is only non-trivial, also called proper. So let's go to example 7. Okay. We're going to talk about a subset of R2. I just did it. Okay, sorry about that. The unit circle, x squared plus y squared is equal to 1. That's the unit circle, not a subspace. Why? 0, 0 is on that. Okay? That's the easiest one to check. Okay? Not on there. But also, you can't guarantee that every point that is on there, like 1, 0, 0, 1 are both on there, but you add them together, they're not on there. Okay. So, I didn't realize the first figure was for example 7, and the last 3 were for example 6. So let's move on to example 8. Which of the following subsets is a subspace of R3? Okay, so now we're moving to R3. That's all of space. Okay, here's A. W is equal to the set of all ordered triplets x1, x2, 1, such that x1 and x2 are any real numbers. I'm going to put that symbol there stands for the real number system. x1 and x2 are real numbers. Okay? B. W is equal to x1, x1 plus x3, x3. Set of all x1, x1 plus x3, x3. Where x1 and x3 are real numbers. Okay. Which of those do you think? A, B, both, or neither? We're talking about R3 now. There's a set of all ordered triplets. Okay? And there's one that's a subset of R3, x1, x2, and 1. Both. Okay? Why?
Because the first even though it have try to make some things like right, it has a 1 for limited values. It can still pass through the origin, right?
Okay? Okay, now the passing through the origin is an R2 thing that we're talking about, but it's still going to be true here, and no, that won't pass through the origin because the Z component is always 1. Origin's down there at 0, 0, 0, so no, it won't. and you just hit Y, it won't. So this one cannot because it doesn't contain the zero vector. The zero vector would be 0, 0, 0.
I was thinking of it as like, if you got, let's say both of those are 0, like x1 and x2.
Right.
It'll just be a point on those yes.
That would be a point. It would be a plane through that point.
Oh, yeah.
That would be the level plane. Z is always 1.
Yeah.
And X and Y can be anything else, but it won't go through the origin. Okay. Yeah. Now, what's even worse or more is that add any two of those together, these x1 to any other x, that's a real number. That's going to be a real number. No problem there. Add x2 to any other real number, and that's still a real number. But add 1 to 1, and you get 2, and that's not in this set, okay? Because that's now up here at 2, not down there at 1. So, and scalar multiple, multiplied by any scalar other than 1, and that won't be in there. This will be a real number. That will be a real number. That'll be C. C is anything other than 1. That's not 1, so it won't be in that set. So it's not closed in vector addition, not closed in scalar multiplication, and it doesn't contain the zero vector. But do those. Yes, because if you add this to any other real number, that's a real number. This to any other addition of two real numbers, that'll be still a real number. That'll be a real number. Okay? Multiply this by a scalar. That's still a real number. That's still a real number. That's still a real number. Okay? Does it contain the zero vector? Okay. Well, to be the zero vector, x1 could be 0, because of any real numbers, and x3 would be 0, any real number, and x0 plus 0 is 0. Yes, it contains a zero vector, so yes, again, B wins. Or last time it was A1. This one is B. Okay. All right. I hope they got that. So the easiest one to eliminate, if it doesn't contain the zero vector, it's not a subspace. Can be a subset, but not a subspace. Okay, but B does contain the zero vector. It's closed under vector addition. It's closed under scalar multiplication. Okay. Now, in example 8, notice that the graph of each subset is a plane in R3, but the only subset that is a subspace is one represented by a plane that passes through the origin. So you're absolutely right. It has to go through the origin, but that one with z equal 1 doesn't pass through the origin. Okay? So now there's 4 conditions for R3. I'm going to leave this up here. You can show that a subset W of R3, subset of R3, is a subspace, SS is subspace of R3, if and only if it has one of the following. Okay? 1. It's only the single point 0, 0, 0. W would be equal to the set of only the zero vector. Okay? 0, 0, 0. At one point, it's closed under addition, multiplication, and it contains a zero vector because it is a zero vector. Okay. 2. W consists of all points on a line that passes through the origin. Or W consists of all points on a plane through the origin. Okay? And 4, W consists of all R3. That's the other trivial. These two are the trivial ones. These two are the non-trivial or proper ones. Okay? So a point that goes through the origin in space is also closed. Everything's fine with that. But a plane that goes through the origin. Any plane or point that don't go through the origin, not going to be a subspace. It won't be a subspace. Will be a subset, but not a subspace. Okay, there's also linear algebra applied. And this is on digital processing on sampling. So I'll let you read through that. It looks a little bizarre, but it's pretty reasonable application. So homework exercises in 4.3. Any of the odds 1 through 5. Okay. They should all be at Calc Chat. Any of the odds 7 through 19. Those should all be at Calc Chat. 21 through 27, they should be at Calc Chat. 29 to 35 should be at Calc Chat. 37 to 41 should be at Calc Chat. True False 43 should be at Calc Chat. And then I would say any of the odds 45 to 49 should be at Calc Chat. There's some proofs, 51 through 59 are proofs. They should be at Calc Chat. You can do any of those. All right. Let's move on to 4.4. 4.4 is talking about, it's two terms here. One we're familiar with somewhat. The other may be new to you. Spanning sets and linear independence. Okay? So let's start with the linear part. We've been talking about linear independence before. This section begins to develop procedures for representing each vector in a vector space as a linear combination of a select number of vectors in the space. That select number of vectors is the important key here. So here is your definition. A vector V. Okay, now remember, this doesn't mean just vectors, okay? This could be matrices, functions, polynomials, all those things we talked about before. But to me, it's easier to think in terms of vectors. Okay, a vector V in a vector space, VS stands for vector space, capital V, is called a linear combination of the vectors now they named the vector V any linear combination of these vectors U1 U2 U3 ... up to U sub K. That's not Britain, that's a different UK. in V, in that same vector space, when that vector V can be written as V is equal to C1 U1 plus C2 U2 plus C3 U3 plus dot 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 up to and including C sub K U sub K. Okay. Where C1, C2, C3, dot, 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 up to and including C sub K are scalars. Okay. What does that mean? All right. Vector V in this vector space, capital V, is called a linear combination of the vectors U1 through U sub K. And these all have to be in that vector space V also. When this V, vector V, I didn't put my vector symbol over it, did I? Okay. When that vector V, let me come back, I hope, yeah, there it comes, can be written as a linear combination. That's what we mean by of those vectors. So, I mean, almost seems like you're talking in circles here, but that's how we define linear combinations before. Notice none of these are raised to powers or anything else. They're all to the first power, and these are just any scales. Okay. That's what we mean by linear combination. Now, there's nothing special about that one yet. We're going to get to some specialness if we can get there. But let's first do example 1. Okay. For the set of vectors in R3, S, okay, and this S is the set of all of these ordered triplets. 1, 3, 1, 0, 1, 2, and 1, 0, negative 5. Okay? These are given the name V1, V2, and V3. Okay. It says here that V1 is a linear combination of V2 and V3. Okay, if that's the case, that would mean, let's write it down just like given, 1, 3, 1 would have to be equal to some C1, or let's call it C2, times 0, 1, 2, plus some C3 times 1, 0, negative 5. Now, it's not guaranteed that's going to be true, but it will be a linear combination of those two if we can find the C2 and C3 that will make it work. So what would that be then? Well, let's do that. That would be 0 C2 plus C3 has to equal 1, right? C2 times 0 is 0, plus 1 times C3 must equal 1. Okay? What's more, C2 is equal to 3, because C2 times 1 is C2, and C3 times 0 is 0. That has to equal 3. Hey, guess what? We just found them. C2 equal 3 and C3 equal 1. Let's see if that works. 3 times 0, 1, 2 plus 1, 0, negative 5. This will be 0, 3, 6 plus 1, 0, negative 5. That would be 1, 3, 1. Yeah, it did. Now, I like to do this little check to it too. Without doing that, here's what else I would have done. It better be true then that 2 times C2, that would be 6, plus negative 5 would be equal 1, and sure enough that's true too. Because if you found out that C2 had to be 3, then that would be 6. C3 has to be 1, that would be a negative 5. So 6 plus negative 5 better equal 1. Okay. This shows for certain. That gives you a good indication it's going to be true. It's a little easier to do, but okay. Now that one was grossly easy. Okay. It was just that easy to do. All right, let's see if we can get B done. Do we have time to do B? Say again? 2 minutes? Let's race and see if we can get it done. Okay? Remember, they don't have to be really vectors. They could be anything like 2 by 2 matrices. For the set of vectors in MTh2, that's matrix 2 by 2 matrices. Okay? What we're wondering is, here is your set S. The set S is a set of 0, 8, 2, 1. I don't think we're going to have time to finish, or I don't think I'll get it written in time. 0, 2, 1, 0, negative 1, 3, 1, 2, and negative 2, 0, 1, 3. There is your set of 2 by 2 matrices. All right. They're set on there. This is V1. Remember, these don't have to be traditional vectors. V2, V3, and V4. Okay? Now they claim here V1 is a linear combination of the other three. V1 is equal to some, I'm going to go and call it C2 again. You don't have to, I'd just like to call it that. C2 times 0, 2, 1, 0 plus C3 times negative 1, 3, 1, 2 plus C4 times negative 2, 0, 1, 3. Okay? And V1 is, why didn't I write this down? 0, 8, 2, 1. Okay? Now for that to be true, I'm going to rearrange order a little bit. That would be negative C3 minus 2 C4 would have to equal 0, right? first entry. That's a 0 minus C3 minus 2C4 would have to equal first entry here, which is 0. Right? That's how you add matrices. Second entry, it doesn't matter what order you do them, 2C2 plus 3C3 is equal to 8. And C2 plus C3 plus C4 is equal to 2. And finally, 2C3 plus 3C4 is equal to 1. All right. How would you do this?
You mean what method you would use to solve it, or just to?
Yeah, how would you go about solving that?
Gas elimination.
Say again?
Starts with G, Gauss elimination. Would it be Gauss elimination?
Yes, Gauss elimination, okay? Absolutely. Now, I'm going to rearrange to do my first step. Is that okay? Because I know what I want to happen first. I want the 1 to be in the upper left. The only thing that's going to give you that is this one. So I'm going to write down 1, 1, 1, 2. And then I'll write the others down. Minus 1, minus 2, 0. 0 minus 1 minus 2, 0. The next one, 2, 3, 0, 8. And the last one, 0, 2, 3, 1. Okay? And just do your row reduction. We're out of time, aren't we? Way over. But that's an easy thing to do. Okay? Relatively. Of course, this one you do minus 2 times this, plus that, gives you a 0 there. You change the signs of these. Go to Gauss. You can either do Gauss elimination or Gauss-Jordan elimination. Doesn't matter. I'll guarantee you one thing. You're going to wind up with a row of zeros somewhere in there because you don't need but 3 of these to make it work. Okay? And but you will find out. And let's see what they. So I can just cheat a little. Ooh. You know what? They didn't even do. Oh, yes, they did. There it is. 1 to negative 1 are the C2, C3, and C4. Okay. They didn't show how they did it. They just said, hey, this works. Shame on them. Okay. But we don't have time for it anyway. So let me give you your last test, which is probably way too easy. And you'll hate me for it. But not challenging you further. Okay. And let me take a look at it and tell you what you can and cannot, or may or may not, or optional or whatever, what we got to do and what we didn't get to do. Okay? So, I know you can do 1, 2, and 3. Those all came from 4.1. Okay? You can do 4, 4, I know came from 4.2. 5 and 6 came from 4.3. Okay. Number 7. Okay. The set is capital S, which shows up at the end of the problem there. You can't do A, so for you may be able to. It's optional. A is optional. B is, that's what we were just doing. So B you can do. We didn't do C. So 7B is required. 7A and C are optional. Okay? 8 is optional. And 9 are optional. We didn't get to talk about spanning or basis and or null space or nullity or rank. So so the ones you have to do, 1, 2, 3, 4, 5, 6, 7B. Those are all the ones you have to do. Optional would be 7A and C, 8, and all of 9. Don't worry about them if you don't want to. If you try them and miss them, they won't hurt you. If you leave them blank, they won't hurt you. I'm grading the ones I said, and anything that you get right of the others, you'll get bonus points. Okay? All right. Try to get them back to me sometime next week. Or this week if you can finish it that quick.
This is the whole weekend right here.
Yeah, I think so. Okay. All right. Any questions? All right. And if you haven't given me your research paper, please get that to me as soon as possible. I'm saying that for everybody listening in case, Peyton, you're listening. So.